In this session, we're going to introduce the most popular clustering method, the k-means clustering method. So you may wonder who first proposed this k-means clustering method. Some people refer to McQueen because he published a paper on the k-means clustering algorithm in 1967. But some other people said Lloyd actually internally in the company published the one in the internal report in 1957. Since the publication was internally published, most people may not even know it. So he republished this one in a journal in 1982. That's the reason some people say Lloyd first got this algorithm. But no matter what, actually the general common thing for this algorithm is they consider every center is represented by the center of the cluster, or we can say centroid. The k-means algorithm essentially can be outlined as below. That means given k the number of clusters, first we can select the k point as initial centroid. Of course, you can randomly select it. That's what the original k-means did. Or you may have some smart way to select it. We will introduce later. Then we can put this one in the repeat anterior loop. That means once we selected this k centroid, we can form k clusters by assigning each point to its closest centroid. Once assigning this, we may need to recompute the centroid because the initial randomly selected centroid may not be a very good one. So we recompute the centroid, that means the mean point of each cluster. Once you recompute the centroid, some object initially assigned to, say, centroid A, now because all the centroid changed, this point may be even closer to centroid B. Okay. That means we need to go back to form k clusters by assigning or reassigning each point to its closest centroid now. Okay. Then we need to recompute the new centroid. That's why we need to get into this repeat anterior loop until some convergence criterion is met. There are different kinds of measures that can be used for calculating the distance and assigning to its closest centroid. Okay. We can use Manhattan distance, L1 norm, or Euclidean distance, L2 norm. Quite often, our initial algorithm was using this Euclidean distance. We can even use cosine similarity. Now let's look at example. How we can execute this k-means clustering algorithm. Suppose we got into 2D space. Initially, there were black points are the initial data point. Then we can, based on the first line of the algorithm, we can select the k points as initial centroid. Now k is 2, we can select the 2 initial centroid. Once we select this initial centroid, we can form k clusters by assigning each point to its closest centroid. Now you probably can see we can assign these black points to either red centroid or to the blue centroid. You can see that's a current assignment. Once you assign these to form 2 clusters, okay, then we need to recompute the centroid. Okay, where you can see you can recompute the centroid. Once you recompute this red centroid, move down here. Okay, then this blue one actually is also moved. Okay. Once we recompute the centroid, we may need to go back to reassign these points to its closest centroid. In this case, you can see the closest centroid, like these blue points, are assigned to the red ones. And this red one is assigned to the blue cluster. Okay? Then we can calculate the centroid again. Okay? So this repeat anterior loop until it becomes stable or until the difference on the different assignment becomes really, really small. Now, the first important thing we should know is this actually is a pretty efficient algorithm for clustering. Because if we total have n objects, we want to find k clusters. Suppose we get a t iteration, it becomes stable. you probably can see the computational complexity is every time every object you need to see which cluster it belongs to. So this time you were assigning to the corresponding k centroid. So that's why it's n times k. In total, you have t iterations. That's why the computational complexity is big O of t times k times n. Usually k and t, number of clusters and number of iterations, is far smaller than number of objects. That's why if you give me n, suppose quite big number of objects, this complexity essentially is linear to the size of n, the number of objects. That's an efficient algorithm. However, k-means clustering often may terminate at a local optimum. Then the initialization becomes important. If you want to find high-quality clusters, we need to have a smart initialization, or we need to randomly initialize this many times, try to find a good clustering results. Another important thing is how to specify k, the number of clusters. We need to specify this in advance for the k-means algorithm. There are many ways to automatically determine the best k. There are some research papers, lots of efforts contribute to this. In practice, you also can run a range of values as k, then select which one is the best. Then for k-means methods, it's quite sensitive to the noise data and outliers. So there are variations like k-medians or k-medoids algorithm try to overcome this outlier or noise data problem. Another thing is k-means actually works only to objects in the continuous, that means numerical data, in the n-dimensional space. How to handle clusters on the categoric data? Actually, people invented an alternative called k-modes algorithm. Another important thing we should know is because we use the sum of the square distance, then it is not good to try to find clusters with non-convex shapes or non-circular shapes. Okay. What you find is something closer to a ball. So we can use density-based clustering or kernel k-means algorithm to do if we get into non-convex shapes. We are going to introduce these algorithms later. So because k-means came quite early and very popularly used, there are lots of studies to work out the different variations of the k-means method. For example, how to choose the initial centroid. Okay. There are methods called k-means plus, intelligence k-means, or genetic k-means. We are going to introduce k-means plus in the next discussion. Another aspect is how to choose different representative prototypes for the clusters. That means we may not use the mean point, then we may use k-medoids or k-medians or k-modes. We're going to introduce this in the subsequent discussion. Another thing is how to apply feature transformation techniques so we may be able to cluster things even they are not in convex shape. For example, there are methods developed called weighted k-means or kernel k-means. We are going to introduce the kernel k-means method.